happens is as we go deep into the Weinstein region, the wave function renormalization gets larger and larger and larger because this combination, which measures how strongly coupled you are, how deep inside the Weissei region you are, gets bigger and bigger and bigger. But at the same time, because the Z is on the bottom here, that's then effectively reducing the coupling of the fluctuations to delta t. So instead of the coupling between matter coming in at the Planck scale, it comes in at a much smaller scale, renormalized by this wave function renormalization. So again, so as long as z is much bigger than 1, that means that the force coming between two delta t's will be negligible relative to the standard Newtonian force between those delta t's by an amount which is proportional to 1 over z. So that's the two ways in which the Weinstein mechanism works to suppress the extra force contribution. Okay. So I'm going to end there. And next time I'm going to discuss how this arises in actual four-dimensional massive gravity theories, and then go on to discuss various other features about the Galilean models. So, are there any questions on this? Finish? Yeah.
G is a renormalization constant, wave function,
Yes.
But if G is so large, then perturbation may not be good.
No, it's the exact opposite. Z becomes large, perturbation becomes better. Because as Z becomes large, then the canonically normalized field, those interactions get smaller and smaller. So imagine we had, think about cubic interaction. Then after we've canonically normalized, then we're going to have square Z to the 3 halves here. So the interactions become smaller and smaller and smaller as the wave function normalization gets larger.
Z is computed at one loop graph of something.
No, this is a tree-level renormalization. I'm using the words wave function renormalization, but this is a purely tree-level effect, right? Because the theory itself has a non-minimal kinetic term. Yeah. So it's not that the loop expansion is breaking down; it's purely tree-level phenomenon. Yeah. Okay. I think that's my.
Questions?
So you checked here, that's the Newtonian effect, right? The higher order effects in general relativity, it's obviously also okay within the Einstein radius.
Right, that's most subtle to check. So here we're doing the check within the decoupling limit, and in the decoupling limit, you're already you're treating the normal sphelicity 2-part to be weakly coupled. So of course, it's much harder to check that the Weinstein mechanism works in the full nonlinear theory. However, Weinstein of course didn't do this argument because he didn't know about Galileons or anything like that. He wasn't thinking in those terms. His argument was much more naive, but the naivety of it was also probably why it works. That he just did the following. He said, let me consider the following massive theory of gravity, where I just brute force, add a Fitzpatrick mass term. And so he said, the VD-VZ discontinuity has to be wrong, at least classically, because there must be some region in which I can treat this equation perturbatively in M. So in other words, there must be some region in which I can neglect this piece, solve the ordinary Einstein-Hilbert piece, and then ask at what scale, how small does M have to be, or how small or big does the source have to be such that this is negligible. And that's what he actually did. And then he showed that generically, if you put the ordinary solution of the ordinary Einstein-Hilbert nonlinear theory in here, the condition for this thing to be negligible is amounts basically to that you're inside the Einstein radius associated with the mass in the system. And that's just a completely nonlinear state. So that's the naive argument that makes you think that the Einstein mechanism will always work.
More questions? One point is not clear to me. Did you say something about the contradiction of the massless limit of the massive gravity and comparing with the Einstein gravity?
Yeah, that's what this is all about, right? So in the massless limit, there is no, this resolves that limit.
Contradiction is at the classical level, even without going to the quantum level.
Yes, and this resolves it already at the classical level.
But including interaction or with even before interaction?
No, you have to have the interaction. So it's the nonlinear theory that resolves the BDZ.
3-point interaction?
Yes, well, it depends on the theory, but in this case it's just cubic interactions. Yeah.
More questions? If not, we'll have a tea break of 30 minutes. Thank you.